And Niko, you can go ahead and introduce yourself and share your screen and get started with your talk.
Yeah, thanks. So, welcome everybody. It's nice to see so many known faces here. I'm happy about this opportunity to play with advanced technology. Let's see what happens. Share, stop, explode, no. Share screen, sorry, here we go. That's actually not what I want to show anyway. Okay. Oh, I had this all set up a minute ago. No, it's... Okay. Okay, so I'd like to try to report on some current paper we have on the... Are you seeing yourselves? No, it's just...
Yeah, we can see.
My screen is screwed up, but okay, I'm happy. Tell me if something's wrong, because I'm not really controlling what's happening.
We can see your handwritten slide that says eCHT at the top.
Yo, that's fantastic. So this is a little less.
But we can't see all the way to the bottom of the slide.
Yeah, that's okay. Okay, thanks. Now let me try to start. Welcome everyone. And I'd like to report on this paper, which is on the archive. You can see depicted here. It's about the Balmer spectrum of the equivariant homotopy theory of a finite abelian group. And it is joined with a number of great people: Tobias Bartel, Markus Hausmann, Thomas Nikolaus, Justin Noel, Nat Stapleton, who is here, and myself. And it's chiefly continuation of last year's Inventionis paper by Balmer and Sanders. And it also builds on some unpublished work of Niels Strickland. So the catchphrase, for those who know what these terms mean, is we're trying to compute the Balmer spectrum of this SP, where do I have to point here? SPG omega. So this is the category of finite genuine G spectra, but I will remind what this really is. And the reason this appeared in the work of Balmer and Sanders, or at least for Paul Balmer, I'm pretty sure that was for him, this was another very substantial, interesting example and instance for his tensor triangulated geometry. So he wanted to study this as much as he can, but I will try to present things from a slightly different angle, trying to put more emphasis on genuine G spectra rather than general tensor triangulated geometry. So let's start with this. So this slide is meant to be an advertisement of the geometric fixed point functors. I will probably assume you have heard something about them. And on this slide, I'm trying to remind that this is these constitute a very powerful tool for reducing equivariant problems to non-equivariant ones. So I introduce the main players first. G is a finite group. And SPG, so I mean, this is supposed to be the category of genuine G spectra, and more exactly, I write this down as a symmetric monoidal infinity category starting from G spaces, space valued pre-sheaves on the orbit category, and I do invert all representation spheres. So this is one way to define this as a symmetric monoidal infinity category. And then I will just name and recall, if needed, that there is a family of very interesting functors, geometric fixed point functors, capital phi of h, one associated with each subgroup. And well, I advertise these as a very subtle and powerful invariant of something G equivariant. At least evidently they map from the equivariant situation to the non-equivariant one. So SP is the category of spectra. And I would just try, or rather I retell an old story, trying to use these invariants to say something meaningful about the Picard group of genuine G spectra. This is something you can always ask if you have a symmetric monoidal category. What are the tensor invertible objects up to equivalence? So this is the Picard group. So I don't mean anything fancy here, not the Picard space or anything. This is really just the group of invertible things. So given these geometric fixed point functors, one thing you can do is, of course, you take your X you want to study and you hit it with all the geometric fixed point functors floating around. And due to the excellent properties of these geometric fixed point functors, namely their symmetric monoidal left adjoints, you know anyway that whatever you get here is going to be some invertible spectrum. And of course, everybody knows the Picard group of the category of spectra. The invertible objects are exactly the spheres. So the group is isomorphic to the integers. So given any invertible G spectrum, genuine G spectrum, you get a bunch of numbers, one for each subgroup. So you get a group homomorphism from the Picard group to the group of maps from subgroups of G to the integers. Okay, now of course you want to know how good an invariant that is, and this is succinctly explained by the exactness of the sequence. So the Picard group, the first thing you can ask, how much information do you lose? What does it mean for an invertible spectrum that all your invariants are trivial on it? So this is to say, what is the kernel of phi? And there are a couple of things which certainly are going to die under these invariants, namely, if you just take an invertible module under the endomorphism of the unit, which is well known to be the Burnside ring, then you can twist the unit itself with this purely algebraic thing, this module under its endomorphism ring, and get an invertible thing. And it's very easy to see that all these fellows die under all geometric fixed points. So this is certainly part of the kernel. And part of the theorem is that it's just everything. And I should say, I mean, this theorem is attributed to many. This just means I didn't want to go wrong in omitting someone, but there are very many people who worked on this in the 70s and 80s. Tumhig, Petri, and May revisited this with co-workers some years later. So it just seemed too dangerous to put specific names because then I'm doomed to forget some. So part of the theorem is that this is a very subtle invariant. It detects almost everything. I mean, if you have an invertible spectrum and all invariants are trivial on it, then the spectrum itself is close to being trivial, or rather it's a twist of the trivial thing by something very understandable. And something more subtle, and as far as I know is open to the very day, is the image of phi. This, I mean, there are lots of partial results, and I think it's known for abelian groups, and I don't know what. This is not meant to be a comprehensive account of the state of affairs, but I'm fairly sure, unless I overlooked something, for general finite groups, the image of small phi is not known. So what I'd like you to take away from this slide is that geometric fixed points functors are a powerful tool to reduce some equivariant problem to a non-equivariant one, namely the Picard group of G spectra is reduced to the Picard group of ordinary spectra. And it does not work perfectly. So in general, we lose some information, some things in the kernel, and we do not exactly know the image. Anyway, this is a nice example of how powerful and invariant these geometric fixed point functors are, and we will now try to play them on another structural problem you can ask for any symmetric monoidal category, namely you can try to classify the thick subcategories, or rather the thick tensor ideals, as I will explain in a minute. Are there any questions? Is everybody gone? Oh, no.
We're still here,
Okay.
and pausing every once in a while to ask for questions is usually a good idea, if for nothing else, to give people a chance to kind of catch up on everything you're saying. So, questions, anyone?
I have a question. Sean Tilson, at the very beginning, you mentioned an infinity categorical presentation of equivariant spectra. Is this completely obvious, or do you have a favorite reference for that? I know there are subtleties in the foundations of these things. So I was just, because
it's not a statement in the first place. I mean, it only becomes a statement if you give me a specific model category and ask me proof that the underlying symmetric monoidal infinity category is this one. But then all instances I'm aware of, like orthogonal G spectra, it's really simple.
Okay.
You map that one in and you have generators, and I think it's easy.
Okay, thanks.
So, more questions so far? Oh, so I try to continue. Oh, now I'd like to use this. What am I doing? Oh, okay. So the aim now is to use these geometric fixed point functors in order to reduce the study of thick subcategories in an equivariant context to a non-equivariant context. So as a first step, I remind you of the non-equivariant results on thick subcategories in non-equivariant spectra. So this is due to Hopkins and Smith. and we fix a prime P, and we denote SP omega P, finite P, the category of finite P local spectra. It goes without saying that this is a fundamental thing in homotopy theory to start at, so I hope you bear with me when I give you this very obvious example of just how complicated category this is. There is no way we will ever classify its object or anything. In fact, classifying even the two-cell complexes means computing all possible attaching maps, which is computing the stable stems of the P local sphere, which produces this little unhappy face. So it's clear there will never be any complete classification of two-cell complexes, but there are coarser equivalence relations we can ask for, and Hopkins asked for. Namely, rather than asking when two finite complexes X and Y are equivalent, we can just ask when one builds the other, meaning X is contained in the thick tensor ideal generated by Y. After all, the thick tensor ideal is just the smallest thing which you can build from the given Y using the obvious structure floating around, meaning this is the smallest class containing Y which is stable under extensions, retracts, and tensoring with anything. This is why it is referred to as an ideal. Of course, that's not an equivalence relation, but it becomes one if you just ask equality. I mean, that's a relation, and you can ask X and Y generate the same thick tensor ideal, then it's an equivalence relation, which is clearly coarser than being equivalent, and you can try to classify finite complexes according to this. And this is what Hopkins and Smith did. So let me remind you of the result. First, there are a couple of thick tensor. There are just a couple of examples of such thick tensor ideals in finite P local spectra labeled C0 through C infinity, and which are just the kernel of the Morava K theories with the usual convention that K0 is HQ, so C0 is everything, C1 is P local torsion spectra, and C infinity is P acyclic, so it's only the contractible ones. I'm working in a P local setting all the time. All the results I'm explaining can be spliced together to integral statements, but that does never add anything really interesting, but lots of potential confusion. So I decided to work in the P local setting all the time. And here's a numerical invariant of a finite P local complex, which will play an important role. It's the type. The type of X is just the largest n for which X is contained in Cn, meaning you just look at how many Morava K theories vanish. And then as part of the thick subcategory theorem, I'm only extracting what I need in the future is the following theorem. I mean this relation of building one another. So X is contained in the thick tensor ideal generated by Y for two finite P local complexes X and Y. It's equivalent to saying that the type of X is at least the type of Y. And in particular, then building the same thick subcategory means exactly having the same type. So this is a classification result. If you classify all the finite complexes by what thick subcategory they generate, the answer is this is exactly given by the type. And then, of course, there's some non-triviality statement which says that for every non-negative number, there is actually a type n complex. So this gives a complete classification of finite P local complexes up to this equivalence relation of generating the same thick tensor ideal. And there are probably no questions, but just for the fun of doing it, let me ask other questions. Nope. Okay. Oh, yes? Oops.
Can you compare the intersection of the Cn's to C infinity?
Oh yeah, that's equal. I mean, I'm with finite complexes here.
Yeah, okay. So
C infinity,
C
infinity is the intersection.
Got it.
Okay. So now, of course, the general thread of the story is supposed to be I reduce an equivariant problem to a non-equivariant one. So I now combine this classical result of Hopkins and Smith with the geometric fixed point functors to approach, well, this here. So this SPC is the standard notation for the Balmer spectrum, but I will unravel what this actually means. So let me just try to use what I've reminded you of until now in order to study thick tensor ideals in genuine G spectra. So I fix a finite group G and a prime P. And just to be clear, P has no relation with the group order. It could be dividing it or not, it doesn't matter. And then I give myself an X, a finite p-local genuine G spectrum, and I attach to it just all the information I can extract from what I've told you so far. I attach to this X a function f of X, which goes from subgroups of G to natural numbers, including 0 and infinity, and it assigns to a subgroup H the type of the geometric fixed point functors. So I remember, given a finite complex G complex X, I remember the type of all its geometric fixed points. And using this terminology, I'm still trying to classify all the objects of compact p-local G spectra up to this equivalence relation of generating the same thick tensor ideal. And there are the following results of Balmer and Sanders on this, which say, firstly, okay, I mean, this relation is still governed by these functions f of x. Like in the non-equivariant case, x is in the x is in the thick tensor ideal generated by y if and only if this function f of x is larger and or equal to this function of f of y pointwise. This, of course, exactly means that x is contained in y if and only if this is true after applying any geometric fixed point factor. So in this sense, again, this containment problem for thick tensor ideals is detected by the geometric fixed points. And then, this is unexplained notation. I mean, the set of prime thick tensor ideals, this is the space. And it's important to understand that this equality here is only as a set. So the set of all primes, we've already also seen. You just pull back the ones we had in the non-equivariant context, these CNs determined by the vanishing of the Morava K-theories under all the geometric fixed points. So this is also part of the theorem. And then, I mean, the problem is not solved. So there are remaining problems, but you can phrase the remaining problem in three equivalent ways. Namely, it's the same, you have to do the same in order to either classify all thick tensor ideals in SPG omega, or to determine which functions f actually are of the form f of x we had before. Or this is the same as to determine the topology on the Balmer spectrum. So I said I don't want to present general TT geometry, so this topology isn't even defined, but in general, Paul Balmer defines this topology on any of these collections of tensor prime ideals. And knowing this topology is equivalent to any of these other two things, except that, of course, the other two things can be said very elementary and without invoking tensor geometry. So this is what I try to do. And also, well, what else? I mean, of course, this is in a sense part B, to give you an idea. In the non-equivariant setting, part B is, of course, arguably the hardest part of the thick subcategory theorem, because, I mean, what's written here is still true for the trivial group and reduces to the Hopkins-Smith theorem, namely determining all thick tensor ideals means determine which functions actually occur, or in the non-equivariant context, this means just determine for which n there is a type n spectrum. This is one of the hardest contributions, that this happens for every n. And this is the generalization to the equivariant context of this is still open for general finite groups G. But it's equivalent to all the other things you could ask. If you're used to thinking of TT geometry, then this is determining the topology on the Balmer spectrum, or even very, very concretely, this is equivalent to classifying the thick tensor ideals of SPG. There could be a possible misconception here, I just realized, so I've not written it, but let me say it. In the non-equivariant setting, every thick subcategory is a thick tensor ideal. This is not true. This is just because the category is generated by the unit. This is not true anymore G equivariantly. So we have nothing really to say on all thick subcategories, but only on the thick tensor ideals. So, yeah, okay. Other questions?
Hi, this is Dan Isaacson. Yeah, I have a question. It seems like part 2 is telling you something sort of definite about the types of of these script f functions that can occur or something, but I'm having trouble sort of unpacking what it actually means.
Yeah, this is also possibly not. If you look back one slide, then the little thing which you're so used to that you don't see it, I guess, are these little inclusions here.
Mm-hmm.
I mean,
yeah.
knowing the topology on such a spectrum is equivalent to knowing which prime ideals contain the containment relation among the prime ideals.
Okay.
And of course, I mean, this is an easy basic fact, but I mean, it's not trivial.
Right.
And it becomes much more so in the equivariance setting when you're asking something like, okay, if my underlying complex has type 5, what are the possible types of the geometric fixed points? This is the type of question which will really turn out to be core. But the formal answer is that just if you just knew the set of these CNs and you knew they were all prime ideals, you would still be far away from having complete answer if you didn't know which one contained what the containment relation is. And in fact, the containment relation is just equivalent data to this topology, because this topology is just a specialization. I mean, yeah, anyway. Okay. Is that an answer?
Sure, thanks.
Yeah. So any more questions, maybe? I realize there are less chances of sneaking away for a second than on a Blackboard talk. I mean, there's no like walking around idly, so it's more challenging. Okay, so let's continue. I mean, by now, of course, I've spoiled everything. There can't be any more surprises now. We just move on to determine what f of x can actually occur. So here's one of our main theorems, and it says assume A is a finite abelian group, and we solve this problem for all finite abelian groups, and for non-abelian groups we have no clue. So let's assume the group is abelian and rename it to be called A accordingly. Finite abelian group, a prime, and any function which assigns to a subgroup some possible types, so natural number between 0 and infinity, then the following are equivalent. There is actually a finite complex, and of course that's a typo here. Sorry. And finite A equivariant complex P local, which has the prescribed types on its geometric fixed points. And this is equivalent to saying that for any chain of subgroups such that the subquotient A double prime over A prime is a P group, there is the following inequality. The prescribed type on the smaller group F A prime is less equal than the type prescribed on the larger group A double prime plus the P rank of this finite group here. The P rank is just the utensile with FP, and then it's the dimension of this FP vector space. Yeah. Just write this. Okay. So, I mean, the slogan here in quotation marks is that the geometric fixed points can drop the type of the finite complex by at most the P rank of the group which is acting. And so okay, are there any questions? I mean, this is like, at this point the talk is over, so to speak. That's our main result, period.
Well, this is Dan again. So, I mean, this is the main result of you and your co-authors, right? Just making sure that.
Oh, sure. Let me.
No, it's okay. I just wanted to make sure. Yeah.
That's it.
Okay.
That's the main result of this preprint, which is on the archive. Yeah, that's true. Nothing else? Okay. So I spent the last. I have many minutes left. Okay, sorry for that. Anyway, I'd now like to say a few words about the proof, but before doing this, I think it makes sense to display this example at the bottom of this page here due to Akil Matthew, which may help to memorize a little bit what this general inequality is about. So it says the geometric fixed points can't drop the type too much, And of course, it's then always relevant to see examples in the extreme case when there's an equality attained. And the easiest example in the easiest case for a cyclic group of order P, you can be very explicit, and this is this example. So let's say the abelian group is Z mod P Z for a prime P, and we produce a finite ZP equivariant complex by looking at the cofiber of the transfer map of the unit. So the unit that's the Generalian G-sphere, and we transfer that up to Z mod P Z plus, go back to 1, and we take the cofiber of this. Then, of course, if you take geometric fixed points of this, the middle term becomes contractible, and the map T becomes 0. Whereas if you take geometric fixed points for the trivial subgroup, which is just a very complicated way of saying you look at the underlying spectra, then the map T is multiplication by P. So if you then pass to the cofiber, you see the geometric fixed points for the 0 groups, the underlying spectrum is S naught mod P, and this has type 1. But the geometric fixed points make this map 0, and the cofiber is in S naught wedge in S1, which has type 1. So this is an example of where the type drops by 1 under taking geometric fixed points. And I should say that already for this very simple group, Z mod P Z, I do not know the explicit example of the type 2 complex with the type 2 complex with a Z mod P action such that the geometric fixed points have type 1. So, I mean, these things, in the end, they are produced by producing some clever examples and feeding this into this general tensor triangular machine, and it's fairly inexplicit. So anyway, this is an example I know about.
Hi, this is Prasit. I have a question.
Yeah.
So does geometric fixed point can increase type?
Mm-hmm.
Okay.
Yeah.
So it's like
Sure.
giving a lower bound, but it can still increase. Okay.
Oh yeah, it's very easy. You can always go up to infinity. I mean, if you can always get this contractible.
Okay, got you.
Let's check.
Hi, this is Sean Tilson. I have another question.
Yeah.
Is the statement that it's not known what an example of a type 2 complex whose geometric fixed points are type 1 for like a generic example for cyclic group of prime order, or like it's not even known for a cyclic group of order 2?
Oh, it's I mean, well,
like, are there some examples that are known, or we don't even, or maybe we don't know?
I mean, it's part of our theorem that there are these complexes, but I mean, the statement was a non-completely rigorous one, meaning like presenting
it doesn't have to be constructive.
Yeah, presenting it as a cell complex, like here. I mean, the cofiber of the transfer map has this property. Now, is there a similar presentation of a C mod P CW complex which does this? It's also, I mean, you can also ask if these things actually desuspend. I mean, the geometric fixed points, I mean, every finite complex up to a little suspension is the suspension of some actual finite CW complex with an action. You could ask to be more explicit about this, but I'm just saying, I just want to point out that these existence statement, we use some very clever and beautiful constructions of Rowan, Lesch, and Mahova as a starting example, and starting from this type of examples, the general TT machine produces the other examples. And this is fairly inexplicit. That was not a mathematically completely rigorous statement. Okay.
Thanks.
Yeah? Oop. Okay, sorry. So then I will just spend a few more minutes to say something on the proof, and I will only talk about the implication from 1 to 2, which I would say arguably is the easier one, but it's the one where we contribute more. I mean, the implication 2 to 1, this is really an existence statement. You're trying to produce complexes with prescribed fixed point behavior, and the key examples we have are really these Rowan-Lesch complexes, which were thoroughly studied by Rowan, Lesch, Mahova, Bill Dwyer did a lot. And this is really hard mod P cohomology computation. and we just feed them into a general machinery and then prove that we get all examples. And it's a little more work to prove that there can't be any more examples. This is the implication 1 to 2. Whenever you have such a complex, its profile function of types on the geometric fixed points has to obey this inequality in part 2. And I'd like to say a few words about why that is true. So can I display that simultaneously? So the first observation is that the proof of this 1 implies 2 reduces to the proof of this statement marked plus, which is that if you have a complex, then the type of the geometric fixed points is bounded below by the type of the underlying complex minus the p rank of the abelian group. So this is some inflation restriction trick. I should say it uses crucially a key observation of Balmer and Sanders, which they baptize as restriction as a type of base change. So it's not trivial, but it reduces to this using things which were known before. So try to understand why such a statement could be true. So how can I control the type of the geometric fixed points if I have information about the type of the underlying complex? So that is this final sheet here. So say I know something about the underlying complex. So I have a Morava K-theory vanishing, Kn star of phi naught of x is 0. So I look at the Lubin-Tate theory of height n, and of course I realize the ecomodulity of x is also 0. And then the collapsing homotopy spectral sequence tells me that also the ecomodulity of all these Borel constructions on x are trivial for all subgroups. But these are exactly the fixed points of one Borel complete type genuine A spectrum, namely, so E bar is the Borel type spectrum, so associated with the Lubin-Tate spectrum, and then you take functions on X on this. This is contractible, which I can evaluate on geometric fixed points. So the geometric fixed points are contractible, and those are this term here. And this is what I'm interested in. This is the finite complex, the type of which I want to estimate. And of course, the finite complex has the same type as its Spanier-Whitehead dual, so I'm happy here. And I'm being told the thing I want to study is annihilated by this geometric fixed points. I mean, this is of course kind of a structural advance here because this expression doesn't involve x. It's just telling me take a Lubin-Tate spectrum of some height n, take some abelian group A, make it act trivially on this Borel complete thing, and take the geometric fixed points, and then wonder what finite acyclics this has, because this is one of the finite acyclics. And this is, of course, this question has been studied in various guises previously in the literature. So this is blue shift for the Tate construction, because it's not exactly the Tate construction, but it's rather the geometric fixed points on the Tate construction. But still, there are many overlapping and similar results in the literature. Again, I haven't made an effort to list them completely, but we made this effort in the paper. And then this theorem is, of course, predictable from what I've said so far. In this situation, if you have a Lubin-Tate theory at some prime p of height n, and you have a finite abelian group acting trivially on it, then this sort of Tate construction has the same finite acyclics as the Lubin-Tate theory of height n minus the rank, minus the p rank of A. So this is where this p rank comes from. And if the p rank is too large, then these geometric fixed points are actually contractible. Okay, are there any questions? So because I'm running out of slides, this is the rest of my talk. This is arguably very terse, but I mean, you can ask if you're interested. I want to say at least one word about how you would approach computing this chromatic height of this E-infinity ring here. You take your Lubin-Tate theory, you take a trivial action, take geometric fixed points. So in any event, this is an E-infinity ring under Lubin-Tate theory, and you ask which finite acyclics you have. And then we use classical beloved knowledge about chromatic filtration, chromatic heights, and so forth. So I go through this in words. The first thing is, of course, I mean, you obtain the geometric fixed points you want to study from this function spectrum, the the E cohomology of A by inverting the Euler classes of all proper subgroups. So this means you have some nice E infinity ring and you invert a little bit. So you, geometrically speaking, you have an open subscheme. And of course here, this is really Strickland's theorem. Maybe I should write his name here. Which provides us with a modular interpretation, so to speak. And actually, this is not very clever. Anyway, let's leave. No, I should. Sorry. Let's not blur these distinctions all too much. I mean, anyway, EBA, this is an even periodic E infinity ring. So really, I care about its pi naught. And then Strickland showed us that this algebra over pi naught of E has a modular interpretation, namely it parameterizes homomorphisms of groups of this abelian group A into the formal group associated with the complex orientation of E. So this is something you have means to understand, homomorphisms of formal groups and so forth. And this happens over pi naught of E, which is just Lubin Tate ring, so power series ring in n-1 variables, and this has this height filtration, so the vanishing of P, V1, V2, and so forth. And to know which finite acyclics this E infinity ring has is exactly knowing through which of these filtrations that this factors or does not factor. So in this way, you make this a purely arithmetic problem about what happens to the universal formal group here when you start inverting Euler classes. Yeah, that's about all I have prepared. I'm sorry, I realize I have very poor timing, but I never did that before, so I didn't make it to 50 minutes, but I'm happy to take questions.
Okay, I'm going to remute everyone, and I will unmute Niko as well for another round of questions. Looks like Sean, you have a question?
Yeah. So Hill, Hopkins, and Ravenel have these symmetric monoidal norm functors that they construct on categories of equivariant spectra. I'm curious if it has been investigated how these interact with the Balmer notion of prime tensor ideals, or if this endows the associated scheme with some kind of extra structure, yeah.
Okay, Sean, I'm going to mute you because there's background noise where you're at. Okay, great. Go ahead, Niko.
Yeah, I wish I had something to say. I mean, is this even an exact functor? I mean, this isn't that only commutes with shifted colimits, no? So why would it even do anything on the Balmer spectrum? Okay, I'm not aware of any results, but I know whom in the audience I would pass this question on to. I'm just not sure I'm entitled to do this. No, anyway, sorry, I have nothing to say about this.
All right, thank you.
Yuri?
Hi, so I was wondering if you can try to play this same game with the genuine fixed points, if you're able to say something about the type of the genuine fixed points.
They're not even finite. I mean, if you think of the Thom-Dieck splitting, the fixed points of the sphere are not finite complexes.
All right. Thanks.
Sure.
No questions? Okay, I have a question back about your main theorem. Could you go back to that slide?
Yep.
Yeah. Okay. So here you're assuming that you're working as sort of in an ambient group A that is abelian, and then you're looking at the quotients, right? This a subquotient, A double prime mod A prime. What if the ambient group A is not abelian, but the quotient is still abelian? Can you say the same idea about about how much the type drops?
I will generalize this question a little and just ask, what do we know about non-abelian groups? that this includes your question. And the answer is that's fantastic. I mean, it's fantastic to see just how immediately everything breaks down if you leave the world of abelian groups. I mean, you can play the same game with non-abelian groups in which every subgroup is normal. And it was to my great surprise that I found out these are actually classified in the 19th century. So these are all like, they're called Hamiltonian groups. Q8 is an example, and everything else is a product with an abelian 2 group. But already for something like D8, the spectrum is not known. And what can I say? Well, why is that plausible? So I mean, we basically have two ingredients. We had these geometric fixed points for the trivial action. So these things were our means to detect non-triviality of something. In the end, that's what it comes down for an abelian group A. These were the cohomology theories which detected our geometric fixed point to be sufficiently non-trivial, and these are always contractible if G is not abelian. So really, there's nothing to say here. And the other implication I didn't speak much about, except to say there are these complexes of Dwyer, Rowan, Lesch, and so these are very interesting complexes with an action of elementary abelian groups, FPNs. And I mean, I'm not aware of anything remotely as precise for non-abelian groups. There are some things for some kinds of semi-direct products, but nothing systematic. You can certainly do things. I mean, for a very specific group, like if every subgroup is normal, it just goes through. But here's another thing which I can say. If you think of this problem in terms of determining how far the type can drop if you apply geometric fixed points, it's actually a huge surprise that this is independent of the type. It only depends on the rank of the group acting. So if this has rank 2, you can always drop type by 2 independent of the type you started with. This is not even known in general for a non-abelian group. So it could be that the same geometric fixed points drop a type 8 complex by 3 and a type 7 complex only by 2, something like that. Mm-hmm. So the non-abelian thing is really pretty open.
Okay, great. Okay, other questions? Okay, if that's it, then I will unmute everyone one more time and we can thank Niko again. Thanks so much.